Okay, let us begin. So there are two versions of the completeness theorem. Yeah, if S is consistent, then S is satisfiable, and if T is a logical consequence of S, then T can be deduced from S. How will you prove version 1 implies version 2? Any ideas? Even if you have not thought about it before, you can think about it now. It's not hard.
Like if you use a contrapositive.
Contrapositive, okay. So we assume that S, yeah, so let us use contrapositive. So suppose there is no deduction of T from S, then
S is consistent, so S is satisfied.
Then S is consistent. Yes. This is simply the definition of consistency, and therefore by version 1 S is satisfiable. Everybody, yeah, I mean, don't write it yet. I will tell you when it is right. And then, why is T a logical consequence of S?
No, T should not be a logical.
Or T should not be a logical consequence, yes. How will you show that? Which valuation? So S is satisfiable, there is a valuation V, and then which satisfies, which models S. See, on our way to this line, we lost touch with T. Okay, anything else? I feel like I spoon feed you on all the answers. Can you use any lemma?
If T is a logical consequence of S, then S union negation T is contradictory. And we can use contrapositive of first one to say S.
Very good. Very good. Okay. So we are not using contrapositive of version 2. We can use contrapositive of version 1. Okay. So suppose T is a logical consequence of S. Then S union negation T is contradictory or unsatisfiable. Okay, then what? Then by the contrapositive of version 1, S union is inconsistent. And then what?
So it can, this proves negation of negation T.
Yes, then by
Lemma.
There is a proof of double negation T, and then what do we use? LA3. By LA3. LA3 and monotonicity. this happens, and as a consequence we get this. Okay, so don't lose track of information. Whatever is given, version 2 implies version 1 now. You have got all the tools, you just have to write a couple of lines, yeah, that's all. I have done the harder part of proving the completeness theorem. Now you just have to play around. Please tell me, we want to show if S is consistent and S is satisfiable. There aren't too many problems in today's sheet, so I'm going to give you time.
We had a quanta positive of this statement, like negation V1 implies negation V2. Like
of which statement? Okay, negation V1 implies, so V1 fails.
So this implies that S is satisfiable. S is not satisfied, but it is consistent.
S is unsatisfiable and it is consistent, okay?
It is unsatisfiable, there exists. Again lost track.
Yeah, I mean, in general that's a good thought, but we shouldn't try to contradict something like completeness theorem. Yeah. Okay, suppose S is unsatisfiable, then what will happen? For
any valuation,
very good, very good. Yeah, because it's always true. Suppose what is the definition of S models T, or T is a logical consequence of S, that whenever there is a valuation which makes capital S true, then it should make T true. But there is nothing which makes capital S true. So therefore, then clearly or by definition, T is a logical consequence of S for all T. Okay, and once this happens, then by version 2 T is deducible from capital S for all T. What does that mean? And by definition, S is very good. This is clearly, see, the length of the proof is very small. You just have to think in the right direction. There isn't much happening here. Okay, good. So let's go to the next one. So we want to prove compactness theorem version 1 and version 2 from completeness theorems. So we have already done one part in the class. Yeah, we have proven version 1 in the class. Now how would you like to prove version 2? Either you can just use version 1 to prove version 2, or you can use completeness theorem to prove version 2.
Completeness theorem version 2 is
Completeness theorem version 2, okay.
So if S models T, if S is a logical consequence, if T is a logical consequence of S, then S models.
So completeness version 2 implies compactness version 2. Okay, if T is a logical consequence of S, then by completeness version 2.
And by finite character of
By finite character lemma, what do we get? That there is a finite S prime deduces T for some finite S prime contained inside S, and hence by what? Hence by soundness. Soundness also has got two versions, version 1 and 2. Okay, hence by soundness we get S prime has T as a logical consequence. So done? Well, I will give you two more exercises that show that version 1 and version 2 are equivalent. Yeah, they are both called compactness theorems. So they are equivalent. And I am not going to spend any time on this right now, but you should be aware of those problems. Okay, lemma 5. This is the simplest one. Has anybody found a solution for this?
Yeah.
Yeah, how many lines is it?
No, I skipped some, like I combined few steps, so I don't know.
Anybody else who has solved this?
Like I used the line and the proof of lemma 2, and like I directly started from there.
Okay, maybe you want to write it. Some of you asked me last Saturday that we have got a long weekend, why don't you give us the assignment sheet early this week? So I worked on that day and I completed the assignment, and now only one person has solved this problem. I mean, where is the first line coming from?
Yeah, so wait, I'll write most of that. Because they can prove anything. And then
Where have you done this? Have we done it in the class yet? Yeah?
It's from lemma 2.
Lemma 2.
Yeah, we can replace.
Okay, yeah?
it's not so good.
From lemma 2. Inconsistency of S comma negation S. Okay, finished?
Yeah, I should write the reason.
Yeah, write the reasons. Does anybody have an alternate proof? Yes, what does it show me? Yes, very good. I want you to write it down afterwards. There is a 3-line proof. Please. As you can see, there are multiple proofs and they all can be valid. You are not using the symbol of turnstile. Huh. Very good. So this is a 3-line proof.
Yes.
And that's, so usually this is a very useful trick when you are working with Boolean algebras. Yeah, the triple negation is always the same as single negation. Yeah, even if you are working in something like intuitionistic logic, when double negation is not the same as the given statement, still this is valid. So therefore triple negation is always a useful thing to remember. Yeah, I mean this is a trick. Okay, good. So let's go ahead. Lemma 4. Let me write down the solution for you. Yeah, this is quite complicated. Okay, so first line. I mean, of course, we have to use dt at the end. This term is quite complicated to deal with. Yeah, S implies negation S. So therefore, it's better to keep it on the left hand side than on the right hand side. Right. So first of all, you can conclude double negation S implies S. What is the reason? At least tell me the reasons. LA3, okay. Second, yeah, then we are going to bring S implies negation S and double negation S. We are going to bring both of them over here, and this is just dt. Okay, third line, we use NLA and MP together. I mean not together, we can write some NLA and then MP. So which one, if I tell you these two reasons, which NLA should I use?
S implies negation.
S implies negation S, very good. So this is NLA. Then fourth one, obviously I should use MP. And on which two lines? 2 and 3. Okay. Fifth one, now that we have double negation S, now we can use, we have S and we have negation S, okay? And whenever we have both of them, what should we use? Huh? Lemma 9. No, lemma 9 is for proving inconsistency. Yeah, that should not be used in any formal proofs. But the proof of lemma 9 use lemma 2. So let us use lemma 2. And monotonicity. So S implies negation S implies, and here we have got a chance to introduce whatever we want. Yeah, because S implies, negation S implies T, where T is arbitrary. Right, so this is our chance, and we are going to introduce negation S implies S, and this is by lemma 2 and monotonicity. Okay, now I'm just going to skip step 6, complete it, and I'm directly going to conclude negation S implies S. Yeah, it's 2 times MP, and then what? We can use dt. Yeah, we can transfer something to. So I'm going to keep S implies negation S on this side, and I'm going to transfer this part. This is dt. What would be the next step now? LF4. Very good. So S implies negation S proves. So double negation S implies negation S implies S. Whole thing implies S implies negation S. Okay, now can you see the final proof? So line number 10 will tell us that with the same left hand side we can conclude S implies negation S, and this is by MP on the above 2 lines, MP 8, 9, and line number 11 we still have to obtain S implies S, and how do we get that? Lemma 1. Lemma 1 and monotonicity, and then line number 12 will get negation S by MP 10, 11, and finally with nothing on the left hand side we'll use dt to obtain this. Okay, not at all straightforward. Yeah, it's difficult to come up with all these things, but I'm sure because we are using something like lemma 2, yeah, we have got lot of ways to do it. Yeah, we introduce something arbitrary over here. Okay, any questions about this? Once you get the solutions, there are no questions. Yeah, but to find the solution, you still need to struggle. Okay, lemma 6. So let me write down the solution for you. What's our ultimate goal here? I mean, as long as we show this, we are done. Yeah, then you just have to use dt twice. Okay, so let us start. So we should use LA3 first. What is LA3? Double negation, elimination. Okay, what is the second step? dt. I am using dt twice. Okay, third step. Lemma 5 with T. What is lemma 5? T implies double negation T. So this is lemma 5 and monotonicity. Okay, fourth step. Now you know what it is. Double negation T, and that's MP on 2. Okay. Then let us transfer this double negation to that side, and now you can see the proof. Yes, how do we eliminate one negation from this? Okay, good. Okay, then seventh. This is just MP on the previous two lines, and then you simply have to use dt. I mean, this goal was not really necessary in that regard. And maybe I can get rid of this. Okay. So you have to learn to play around with axioms, and that's the only way to do it. Any questions?
Okay, so I'm going to do question 7 on the board. I hope you've all read it because it's a long question. But it talks about something called graphs. How many of you have seen graphs before? Not the x-axis, y-axis graphs, but the vertices and edges graphs. One. Okay, not a lot of people. So I'll talk about what a graph is first. So the formal definition has been given in the question. The formal definition of a simple undirected graph. So it's given by a pair, which consists of one. So the question tells you that a graph is a pair v comma e, where this is a set of vertices and this is a set of edges, which is a subset of v cross v. But that kind of notation is not very easy for human beings to work with. Maybe a computer would like it. So what we generally work with is the drawing of a graph. So what you have is a set of vertices, which you denote using points, and you can label them if you want. And then you have a set of edges. Now you've been given some nice properties about the set of edges, that it is irreflexive and it is symmetric. Yeah, and it's going to be a subset of v cross v. So what you do is that whenever you have an edge in E that looks like 1, 2. Suppose 1, 2 is in E, then you just draw a line between them. Because you also know that 2, 1 will be in E because of symmetry. So you can do nice things like this. If 2, 3 is not in E, then you don't draw this line. If 1, 3 is in E, then you draw this line, and so on. So this graph is going, this drawing is going to denote the graph 1, 2, 3, 4. And the set of edges will be 1, 2, 2, 1, 1, 3, 3, 1, and 3, 4, 4, 3. Maybe I'll add one more edge. 2, 3, 3, 2. So things like that. Any questions about this? So this is a very small example. The question actually asks you to prove something that is also true for infinite graphs, which you can't really draw. Okay, now also the question deals with the coloring of a graph. So Again, the formal definition is given there, but what does a coloring really mean? You have a set of k colors, so maybe I'll take 2 colors. So my k equals 2 here. And what you do is you assign a color to each vertex, such that if 2 vertices are connected by an edge, they don't get the same color. So say I color this yellow, that means I can't color 1 and 3 yellow because they're connected by an edge. So maybe I can color them blue. And I can't color 4 blue because it's connected to 3, which is already blue, so I'm forced to color this yellow. And now this is a valid 2 coloring of this graph, blue-yellow coloring. Of course, you can't always color a graph nicely. For example, if I give you this graph, can I color it with 2 colors? Let's try. So the first color you can just assign randomly, right? It doesn't matter. That forces these 2 colors to be different from yellow. So if I colored this one blue, I can color this neither yellow nor blue because it's connected to both of them. So I can't color it with 2 colors. Can I color it with 3 colors? No, again no, because if I give this the color red, then I won't be able to color this anything. In fact, you have something called the chromatic number of a graph, which is the minimum natural number k, such that you can color the graph with k colors. Yeah.
No, 1 and 3 are colored the same in the first example.
I'm so sorry. That's very silly. Yeah, I messed up here. This graph is not 2 colorable. You would need 3 colors. Yeah, I'm very sorry about that. I didn't see that last edge. Okay, so now you have 2 choices for this vertex 4. Either you can color it red or, blue or yellow. Yeah, so this graph is also not 2 colorable, but it is 3 colorable. This graph is 4 colorable. Also the question mentions subgraphs. So what is a subgraph? Well, you have this graph, and you get a subgraph by removing some vertices and edges. But of course, if you remove, for example, if from this graph I removed vertex 2, but left these 2 edges, it would make no sense because the resulting thing would not be a graph, right? Because the set of edges has to be a subset of V cross V. If I remove this vertex, then 2 isn't in my vertex set, and so you can't be having these edges anymore. So what is a subgraph? A subgraph G dash of G will be a set V dash comma E dash, where V dash is a subset of V, and E dash is going to be a subset of E such that you are only taking edges of which the vertices have survived. So E dash is also a subset of V dash cross V dash. So then this would be a valid graph, right? So in this case, if I wanted to remove this vertex 2, then I would also have to remove the associated edges. And maybe I could also remove this edge if I wanted. Then I would be left with 3 vertices and 1 edge. So this is a valid graph. Any questions about what a graph is, what a subgraph is? You will probably be encountering graphs a lot in your stay at IIT and later. So this was a short introduction. Now we can dive into the question. So the question asks you to show that a graph is k colorable if and only if every finite subgraph is k colorable. And you have to show this using compactness. So is one side of this obvious? If a graph is k colorable, every finite subgraph is k colorable. What happened? Okay. what happened here? I removed some vertices and edges with the coloring, the subgraph and the coloring that was left. Is this a valid 3 coloring of this graph? Right? Do you think this would hold in general, that if I take a graph and I take a subgraph of it, if the original graph was k colorable, should the subgraph also remain k colorable? Yeah? Right? Okay. So that means that one side is obvious. If a graph is k colorable, then every finite subgraph must be k colorable. In fact, every subgraph will be k colorable, even if you remove the finiteness condition. So, any questions? Fine. So I haven't done that part. You can write that part on your own. I am more interested in showing you how to do the other side, which is that if every finite subgraph is k colorable, then the graph is k colorable. And you have to use compactness, which means that you would need to define the language and the set of formulas that you will show finite satisfiability of and proceed. So the question also gives you a hint. You start with defining a set of propositional variables. We'll call that set L. This consists of Pxi, where x iterates over the vertices and I iterates over the colors. Yeah, I haven't written the meanings of this because most of them are in the question, but what Pxi intuitively should denote to you is when you define a valuation in Pxi, if it's true, that means that you're assigning the color I to the vertex x. And if it's false, then you're not assigning that color. So that's the meaning of that Pxi that you should keep at the back of your mind. And then you define a formula for each vertex. You define Sx, which says what? You want Sx to denote the fact that the vertex x receives exactly one color, right? So for k colorability, that is one condition, that each vertex receives exactly one color because it's a function. It's given to be a function. Therefore, each element of the domain needs to receive exactly one element of the range. So this is what that formula denotes. What it says is that it's the join of all the Pxi's. So where I iterates over the colors while x is fixed, right? So this tells you if you want the formula to be satisfied, you would want at least one Pxi to be true, which means that your vertex x receives at least one color, right? Is anybody lost? Okay. So that's the first part that's done. The second part should tell you that a vertex doesn't receive more than one color, which is exactly what the second thing is doing, that for each I less than j, so I and j are colors, it does not happen that both Pxi and both Pxj are true. So the vertex doesn't receive both the color I and the color j, where x is not equal to j necessarily. Right. So Sx intuitively should denote the formula that each vertex gets exactly one color. Any questions? Okay. Now what is the second thing that you need for a coloring? The second.
So the neighboring vertices should have.
Exactly. So then for each edge, you would like to define a formula that captures that notion. So for that you define Txy. So Txy says that Pxi happens if and only if Yi doesn't happen. And you define this for all. I mean, I haven't even said what it's defined for, but we'll come to that later. Intuitively, what you should think of this is that if x and y are endpoints of an edge, then for each color, x receives a color if and only if y doesn't receive a color, or vice versa, right?
No, how is it if and only if? It should be only if.
It would not matter because you would have Txy and you would also have Tyx. So even if you wrote this and included all of these formulas, it would be fine because you're given that the graph is symmetric. So this would work, but this is more intuitive to me, so that's why I'm writing it like this. Okay, so now you'd want to define your set of formulas which captures that your graph is k-colorable, right? So that's the idea that you have in mind when you're defining the set of formulas. So first thing you need is for every vertex to have a color. So for each vertex you include the formula Sx. And then for each edge x comma y, you include the formula Txy. And also, I mean, because E is symmetric, Yx is also going to be here, so Tyx is also going to be here. So as Sriram said, you don't really need both sides. You can have one and it would be fine. Any questions still here? What is this set S? Does everybody understand why we have defined S like this? Okay. Now, we've shown one side of the argument, we have to show the other side. We have to show that given that every finite subgraph of G is k-colorable, you want to show that G is also k-colorable. So let's take that hypothesis. Suppose every finite subgraph of G is k-colorable. Now, does this automatically give you that S is finitely satisfiable? How many people say yes? And how many people say no?
No.
Why do you say no?
Because like any collection of those statements won't necessarily like describe a subgraph.
Exactly. So maybe you have this subgraph, maybe you have your T corresponding to this graph. I'm defining something. So maybe you have or not okay, suppose our graph is this, and then we also have these other things. So suppose that my finite subset of S contains the formulas S1, S3, T1, 2. But this doesn't really correspond to any subgraph of this, right? Because it doesn't have the vertex 2 in it. For this to define a subgraph, you would need, if you want to draw a graph corresponding to this, you would have 1, you would have 3, and then suddenly you would want that edge that connects 1 and 2, but vertex 2 just does not exist. So what are you going to do about it? So you can't directly use compactness, you have to do a little bit of work. Okay, suppose that S0 is a finite subset of S. So you have a finite subset of formulas, and let V0 be the set of vertices that are either in S0, such that Sx is in S0, or such that some formula Txy is in S0. Why don't I need to include Tyx here? It's symmetric. Okay. Now I want to define a larger set of formulas such that my set of formulas will actually describe a subgraph, a valid subgraph. So you define S1, which has all Sx where x is a vertex in V0. And it also has all the edges that are in E such that both vertices lie in V0. Is this a valid subgraph? I've just enlarged it. So if I wanted to perform this operation on this set, then if this was my S0, then my S1 would look something like S1, S3. I would also add S2 because this 2 is over here, and then I would have T1, 2. Would I have something else also? I mean, okay, it'll become a bit larger maybe. I would also have T13. I don't need to include T13, but okay, the way I've defined it, it would. But things will work fine, so it doesn't matter. So now you define your subgraph to be exactly the one described by this. Your set of vertices and your set of edges being the ones that are here. And since V0 is finite, since your vertex set is finite, and your edge set is a subset of V0 cross V0, your entire graph is going to be finite. So this is a finite subgraph of G. By our hypothesis, it is k-colorable. So what does that mean? There's a k-coloring. So there's a function from the set of vertices to the set of k-colors. And now, how from here do we say that our S1 is satisfiable? We want to define a valuation on the propositional variables. We define a valuation that gives we now use the intuition that we had at the back of our mind. We say that Pxi is true if and only if we have assigned our vertex V a color I. Does that make sense? And then you can check, you should check this, that S1 will satisfy, the valuation, I wrote it the other way, I should write that the valuation V satisfies S1. Right? Okay, we can check that it satisfies these formulas. That means that S1 is satisfiable. And since S0 is a subset of S1, S0 will also be satisfiable. And since S0 was an arbitrary finite subset of your formulas, you can conclude by compactness that S is going to be satisfiable. Any questions? Any confusions? This is not the end, because you have to still say that your graph G is k-colorable, but I have left that to you. Why does this valuation correspond to a k-coloring of G? You still have to define this k-coloring. You need to define chi dash from V to K, which is a valid coloring. And therefore, you can conclude that your graph G is k-colorable. Any questions?
We cannot use that directly because that is not a valid subgraph.
Yeah, because you want to use that every finite subgraph is k-colorable, but if your set of formulas doesn't correspond to a graph, then you can't use it.
S1 and everything.
Yeah.
Every subset of S1 is finite.
Every subset of the S1, you defined a graph using S1, and you said that since S1 corresponds to this graph and this graph is a finite subset of G, it is k-colorable, and therefore S1 is satisfiable. And therefore the smaller subset is satisfiable. This was a lot of stuff because I also defined graphs for you. So any questions here? Okay, then we are done.